So hello everyone, this is Cyberdash where we dash into data. Now today we have a different sorting algorithm called counting sort. Think of this as like this. What if you could sort numbers without comparing them at all in non-comparison based? So counting sort is a non-comparison based algorithm which unlike bubble and quick sort, it doesn't compare elements to each other. Instead, it counts how many times each value appears. For example, let's take um, like you're working with integers and the ranges of those values are small. So at that moment, speed is the key thing that really matters. Common users like using this algorithm, uh, let's take sorting exam marks, frequency based problems, and sorting ages, IDs, ratings. And but there's a catch. We'll get to that later. Now let's dive into what is the key idea and what is the introduction of what this quick sort really means. So counting sort, no sorry, counting sort. Yeah. So counting sort is a non-comparison based sorting algorithm. It is particularly efficient when the range of input values is small compared to the number of elements to be sorted. So the basic idea or the key idea behind counting sort is to frequency is to count the frequency of each distinct element in the input array and use that information to place the elements in correct sorted platforms or positions. So it works well with the range of input values is small and comparable to the size of the array. For example, let's take an array of 1, 4, 0, 2, 1, 1 with a total of 6 and range of the values are 0 to 4. So if range of the input array is order more than n log n, where n size of the array, then we can better sort the array using standard comparison based like merge sort. So yeah, you guys are familiar with merge sort so well. So this is the key idea behind it. So when declaring a count, or in this counting sort algorithm, when we declaring a count array, we name it as count array of size max array plus 1 and initialize it with 0. Yeah, the first element always start with 0. So then we traverse the input array and map each element of array as an index of count array, and then we execute count array plus plus for 0, which is less than I or equal to I than n. Then we calculate the prefix sum at the very index of count array and create an array with the size of n and traverse array from end to update. So why do we compute prefix sums? We could simply count the occurrences of all elements one by one, put them into output array, but we compute a prefix sum to achieve stability in this algorithm. Now this is the key point actually. To achieve the stability in this algorithm, note that after building the prefix sum count array, we traverse the array from right to end to ensure that the last occurrence of moves to the last corrected position in the sorted array. So guys, actually my video doesn't work, uh, so I had to turn off the camera because it doesn't actually work. Some sort of software problem is there. So pardon me for not videoing myself, but I'll go through this very well, and you don't have to really care about it because due to a technical problem, my video doesn't work. So that's all. That's enough things, and let's dive again. So this is how the counting sort actually works. Now we'll take this. Find out the maximum element from the given array. Now this is the array we have, and the max element is the 5. Alright. So as the second step, we initialize the count array. of length max plus 1 with all elements as 0. Now this is the count array. This array will be used to store in the occurrences of the element of the previous or the input array. So next we have is the count array, and we store the count of each unique element of the input array at their respective indexes. So you can actually see 2, 3, 0, 2, likewise here it have been stored, and 5 is not here. So then we store the cumulative sum of the prefix sum of the elements and the count array by doing count array I equals I minus 1 plus I. That likewise we get the count array like this. Then we update it. Likewise, now 3 is here, then 3 comes here, and minus 1 means 6, and then plus 1 again 7, like that. Likewise, we get the ANS array. Then we update it with that equation where array we get a element and then minus 1. Likewise, we update it like here, and likewise the updating happens. And then here we get the full ANS and max as 5. Now max was at the here. Now max was at the last element, which is the maximum element. Then we add it here. So likewise, now this is the code for the counting sort. There's not much to consider about it. Now this is the key point when taken counting sort. Complexity analysis of counting sort. Time complexity, or n plus m in all cases, where n and m are the size of the input array and count array respectively. Auxiliary space, or n plus m, where n and m are the space taken by output array and count array. Now this is the difference between this input and output time complexity and auxiliary space is in all cases n and m are the spaces taken by the specific array, the input array or the output array. That's the difference between time complexity and auxiliary space. So when taken advantages, counting sort generally performs faster than all comparison based sorting algorithms such as merge sort and quick sort. And this is a stable algorithm. Now when we take merge and quick sort, that requires a many large number of steps. So when taken counting sort, this doesn't actually go that much deep because it generally performs faster than all comparison based algorithms. And note, this is not a comparison based algorithm. The merge sort and quick sorts are, so this is a sorting algorithm, but it is not comparison based. Now what they say here is counting sort is generally faster than all the comparison based sorting algorithms out there, like merge sort and quick sort. That's all. And this is a stable algorithm, that's all. So the disadvantage is this actually doesn't work on decimal values. For example, like we discussed in this workings, if there was a decimal value, then it won't work because it's literally obvious. And next up we have is inefficient if the range of values to be sorted is very large. Yes, when the range is very large, we can't actually sort because it is not efficient and not an in-place sorting algorithm. It uses extra space for the sorting and the years. Now we had to draw a count array, an ANS array. Likewise, we have to draw some. It takes a lot of space. By the way, but it's faster. So as the applications we have, it is a commonly used algorithm for the cases where we have limited range items. For example, sort students by grade, sort event by time, days, months, years. For those application, we use counting sort. Uh, some say that it is a subroutine of radix sort, which is another section. And the idea of counting sort is used in bucket sort to divide elements into different buckets. Yeah, the when we take bucket sort, it means like it is also derived from counting sort onwards. Now this is the whole idea, whole theory behind counting sort. Now I'll actually show you some interview questions based on counting sort. Now, what is counting sort? We actually talked about what is counting sort. It is a non-comparison based sorting algorithm that operates in linear time, making it faster than any comparison based sorting algorithms out there, like merge sort and quick sort. So, what is the time complexity of counting sort? The time complexity of counting sort is O n plus k, where n is the number of elements in the input array and k is the range of the input. Now, what is the space complexity of counting sort? We actually talk about it. Space complexity of counting sort is the where is O into k, where k is the range of the input. And under what conditions counting sort is most efficient? It is most efficient under the range when the range of input elements, which is k, is not significantly greater than the number of its elements to be sorted. How does counting sort work? We actually show an step-by-step explanation on how counting sort works, so let's skip that part. Can counting sort be applied to non-integer inputs? Yes, it can be applied to non-integer inputs, but not into decimals, because that's a disadvantage we have. What is the main advantage of counting sort compared to comparison based algorithm? Counting sort has a linear time complexity, which make it faster than all the comparison based algorithms out there. That is an advantage we have, and it can be also taken as a characteristics of one characteristic of what counting sort is. So what happens if the range of the input elements in counting sort is very large? If the range of element is of counting sort is very large, it may not be efficient in terms of both time and space complexities. We actually this is a straight up disadvantage we have. If the range of the input element is very large, it is inefficient to sort it actually. Then the next up we have is, can counting sort be used for sorting floating point numbers? No, counting sort is not designed for sorting integers. It relies on integer keys for indexing into arrays. How does counting sort handle duplicate elements? Duplicate elements are handled by incrementing the count for each of an element during counting phase. Now this is the stability property of counting sort. Counting sort is a strong and stable sorting algorithm by preserving the relative order of equal keys. Now that's the stability point of counting sort. Is counting sort not the fastest? Counting sort runs in O into the brackets n plus k time, and making it asymptotically faster than comparison based algorithms out there like quicksort and merge sort. Now that's up we have to discuss, and it is not a in-place sorting algorithm. Now this is also a key point we need to see. So these are the common application where we use counting sort. Counting sort is often used in a situation where the range of input values are actually relatively small. and such as sorting grades, frequency of elements, characters in a string. It is also used as a subroutine of in other algorithms like quick sort. No, sorry, radic sort. So this is the whole idea and the whole introduction about what quick sort really, counting sort really is. So we'll dive into code later. Now, since you guys uh, gained a simple logic or a stable sorting something about what real counting sort is, so that's up we have as the application, the advantages, disadvantages, how it works, key idea behind it, and how arrays works when taken into counting sort, the characteristics, the introduction, and all. So counting sort isn't perfect actually, but when used correctly, it is insanely powerful. If this helped you understand sorting better, so hit that like button, subscribe to Cyberdash, and I'll see you in a next deep dive about what really counting sort and how it actually works in real life scenarios. So thank you for listening and have a good day.